This is a problem from chapter number 5, problem number 40. And we're starting to look at force diagrams and how we can read them. And so as we look at this, we see two forces that act on this block. We can also draw in additional forces that we know about, and that would be, we have M times G down, and we would have a normal force. That's up, force normal, and we can calculate all of these values, but notice what it's asking us for. It wants to know the acceleration of the block, and so immediately that says, let's add up all the forces to find the mass times the acceleration. And what this really means is that we do this in both the x and the y direction, just like with projectile motion. So this is really two equations. One is add up all the forces in the x direction to give me mass times acceleration in the x direction, and then add up all the forces in the y direction to give me mass times acceleration in the y direction. The first thing to note here is that because it started from rest and it's not going up or down, it's continuing to have zero acceleration in the y direction. And if we're just trying to find the acceleration of the block, we can really focus our attention on the x direction. And so that's what I'm going to do. I'm going to redraw this as a force diagram right on this point. So we have a force, let's call this force 1 and force 2. So I have force 1, which is 30 newtons to the right. And then we have another force that's coming down here, which is force 2. It's also 30 newtons with 30 degrees. Lots of 30s running around on this. And then, of course, I have normal force, and I have mg. And these are probably not drawn to scale. In fact, I'm sure they're not, because the mass is 10 kilograms, so this mg would be 10 times 9.8 or 98, and these arrows are 30. So if I'm strictly speaking, I should really make this a lot bigger. mg. And then let's make this bigger as well for normal, to kind of give it a little better scale. So the forces in the x direction, though, that we're interested in are just this force 1, which is 30, and then the x part of this. So if we draw that again, and I'll just put it here sort of in the middle. Okay, so there's our F2, just so we get used to this, because we've got some more SOHCAHTOA coming at us here. This force 2 has a component that is in the x direction, F2x, and F2y. And I can redraw that F2y like that. And so I need to find the components. And so as I do this, I notice that cosine of 30 degrees is equal to F2x over the magnitude of F2, which I'm just writing as, you can write it like this, or you can write it as magnitude of the vector. Either way works. And so F2x is just going to be the magnitude of the force times cosine of 30 degrees. And now I think we have all the forces that we need in the x direction, because I've got two of them. I've got F1 plus, I've got now F2 cosine of 30 degrees is equal to now m times a in the x direction. And let's check. This I know is 30. That's 30 times cosine of 30, and my mass is 10. And so I can find the acceleration. So I've got 30 newtons plus 30 newtons times cosine of 30 degrees is equal to 10 kilograms times the acceleration. So I can divide the whole thing by 10. And this gives me, if I put this in, I've got 30 newtons plus 30 newtons times 0.866, all of that over 10 kilograms equals my acceleration. Remember that newtons, of course, are kilogram meters per second squared, so a newton And Newton divided by kilogram gives me meters per second squared, which is what I want to see. And so if I plug all of this in, this is 30. This is 30 times 0.866, 2.25-ish or so, divided by 10. You add all of that together, you put it in your calculator, you get an acceleration of 5.6 meters per second squared. And that's the answer that they're looking for. Okay? What's the acceleration of the block? But we can go one step further and learn a little bit more about this just by looking at what's happening in the y direction. And I think it's instructive. So if we look at what's happening in the y direction, remember our acceleration in the y direction is 0, but we can go ahead and add up our forces in the y direction. And those are force normal is up minus mg, but that's not all. Notice that we have this little piece. And that little F2y is the opposite to that angle. So if we look again at this picture right here, we can see that, I'll redraw it over here. Here's my F2. This is F2y. This is theta. So F2y, you can check, is equal to F2 sine of theta, because sine of our angle is F2 divided by the hypotenuse, so sine of 30 degrees, and it's pointed down, so I'm going to say minus F2 sine of 30 degrees is equal to 0. And what this allows us to do is actually find the normal force. And the reason I wanted to do this is a case where the normal force is not equal to the weight. It's actually a little bigger, right? So I need to make sure that I draw this just a little bit bigger than the weight, because it's got to account for the y component of this. If I call this F2y, these two things added together need to equal that. So in other words, this and this, these two pieces need to equal the orange going up. And that's exactly what this equation is giving me. So if I plug all the values in, I can find that the force normal is equal to mg, in this case, plus F2 sine of 30 degrees. And F2 is still 30. This is a 30 times sine of 30. That would be a 1/2, 15. And this is 10 times 9.8. So this is 98 newtons plus 30 newtons times 1/2 from the sine. And so my normal force in this case is equal to 113 newtons. So it's bigger than 98 by 15, obviously. And so the point here is that your normal force is not always equal to your weight, and sometimes you just have to do F equals ma to figure that out. Again, this question didn't ask for it, but an extension could be, what's the normal force?